Hey, good morning, good afternoon, good evening from wherever you're watching us. My name is Sinisa and I'm the Director of High Performance Computing and Artificial Intelligence for Lenovo. Today I'm welcoming you all to the first in a series of quick-fire discussions with some of the world's leading researchers in genomics and computational biology, where we're going to discuss how today's socioeconomic environment is driving absolute need for a sustainable and innovative technology roadmap. And it's going to address humanity's greatest challenge. So today I'm joined by Dr. Harsh Seth, the head of Advanced Genomic Technologies Division and assistant professor at the Institute of Human Genetics. He specializes in cancer genetics, genomics, chemoprevention, molecular diagnostic genetics, and cytogenetics. Wow, that's a mouthful. Hi, Dr. Harsh, welcome to this morning's discussion.
Thank you. Good morning, good afternoon, good evening to everyone who is on board. It's a pleasure to be here, and cheers, Sinisa, for that wonderful introduction. I think what we are planning to discuss today is about how genomics as a field is advancing not only just healthcare, but is driving sustainable innovation across a whole variety of sectors, be it computing, be it farming, be it climate change. So all of those sectors, genomics has a big role to play. And just like any other sector, computing has a big role to play in driving the genomics revolution forward.
No, you've actually made it a lot more succinct than I did. So look, why don't we just kick off? So Doc, what do you see are some of the critical factors to deliver this sustainable and resilient ecosystem? And how can we improve the quality of human life?
I think we kind of have to scan back how genomics revolution started. And for that, we have to go back to the 80s and 90s, whereby when you did sequencing, right, you kind of had an X-ray photograph in front of you, and somebody would actually sit down manually and would read every single letter by hand. And on a very good day, a scientist could read about 400, 500 letters of the DNA if they were really good at it. And you have to remember that there are more than 3.3 billion bases in the human genome. So that is why it took more than 13 years to read just one complete genome of an individual. And it used to cost $3 billion back then.
Right.
By 2007, though, a lot of technologies came on board, including the computing revolution, right? So the chips went much more faster. You could analyze much more data. There were far more threads and far more memory to analyze all of that data together. So by 2007, you could do a genome of an individual within 6 months period if you had a really good architecture in front of you. Today, however, you can do genome sequencing of an individual in 2 or 3 days' time, and it would cost you $1,000 to do that. And in that one particular leap, in a span of 30, 40 years, we've gone from having a cost of a genome of about $3 billion to less than $1,000. Now, if you kind of think of it in computational terms, we have already broken Moore's law since 2007, and it's much, much, much faster today than it ever has been.
Well, look, I agree with you 100%. Moore's law has disappeared. This advanced technology, as you said, chips speeding up, the advancement with GPUs, accelerated technologies, has just destroyed Moore's law completely. And we're able to do so much more, not just in the genomics field, but across high-performance computing in shorter times with more data, with more levels of granularity, I think.
Absolutely. And of course, for the past 3 or 4 decades, it's been a dream of a scientist to provide, or even a doctor to provide, result to a patient within a reasonable time frame whilst they are in the clinic. And in these 3 or 4 decades, the pace of advancement has been so huge that now we are getting to a point, I believe, that we can provide a genetic test result to an individual within a few days' time, or in some instances, even within a few hours' time. And all of that has been down to not only just the revolution that has happened in genetics, but computational biology has also played a major role. Because finally, we are seeing an intersection of physics, chemistry, mathematics, and new silicon wafers that are coming through. So it's a great time to be alive.
Yeah, it is. It is indeed.
So Sinisa, based on our discussion earlier, what sort of technological barriers or innovation barriers do you see that are halting the genomic revolution right now?
Well, look, organizations generally have limited time and limited resources to develop some of these genomic technologies, right? And are relying more and more on specialist organizations. You know, in fact, Lenovo and Intel commissioned a study by IDC on decoding genomics with smarter IT. And it highlighted that I think it was like 28 odd percent of Asian respondents selected that a solution is not scalable as one of the most top reasons to evaluate changing their technology infrastructure or changing their HPC infrastructure. You know, 20 odd percent said too much customization or solution is very complex, which goes to the first thing I said, which is most organizations have limited time and limited resources. What they really want is sort of, I guess you want to call it a prepackaged blend of these technologies. So, you know, Lenovo has a long and storied history in HPC and a very strong focus in genomics. So to that end, you know, using your timelines that you were talking about a little bit before, we actually worked with Intel on the GATK open source code. And we optimized and tuned that for our hardware base, not using accelerators, by the way, which are very expensive generally in the market today, but doing that on off-the-shelf componentry. And we call this piece of genomics, I guess, an appliance. We called it Ghost. Now, in essence, I don't want to get into the technical, but we've been able to reduce processing time of a whole genome sequence or a whole human genome sequence in this case from 60 hours, 150 hours, depends on where you're running. That's why I've got a spread, nearly a double spread of hours, down to roughly anywhere between 24 and 48 minutes. Wow. Supremely optimized and tuned for this. So again, the essence is that Ghost improves lab productivity. It improves time to data. So you get answers faster, your discoveries potentially could save more lives. So it's these technology innovations like Ghost, which we're using and selling in the marketplace today. And that's begun the process of democratizing knowledge, which is important, right? Not democratizing a process, but democratizing knowledge. Because you can actually have these units and have these appliances positioned in wet labs, in smaller laboratories, not just massive farmers that are the only guys that used to be able to do it, or highly funded research institutes.
So what you're saying is that the way to go through the bottleneck of the genomics revolution right now is to actually democratize access to these wonderful technological advancements in computing that are now coming through, and that will drive the revolution forward.
Oh, absolutely! It's the only way to do it. Knowledge is power, and what a lot of people say today, a lot of organizations, a lot of reports on this. Knowledge and data, well, data builds knowledge, is the new oil. Yeah. And being able to utilize that efficiently, quickly, is the only way to advance humanity, to be able to attack humanity's greatest challenges.
That's absolutely true. Actually, Sinisa, you make a very interesting point, because what the sort of infrastructure that you're describing is what I would like to call a hub and spoke model, whereby you'd have a centralized laboratory infrastructure where hundreds and thousands of genomes are analyzed day in, day out, and you really require a scale to analyze all of that data. But on the other hand, you have a point of care model, right, whereby you want the results to be delivered right then and there to the patient. And come to think of it, about 3 or 4 decades ago, everybody thought that we would only require 4 or 5 computers ever. And now computers are everywhere. We wear it on our wrist as well. And come to think of it, my mobile phone has more computational power than what people had for Apollo 11 mission. So clearly we are getting to a point of not only just having these massive hub and spoke models, but having more point of care models as well. These are not necessarily speaking contrasting models, but they do work with each other. They're asking different questions, but they all require the computational power that you mentioned.
Right. Again, good. It's a good point. So based on that, and based where you were sort of going, what type of level, or traditionally, what level of impact has genomics had across some of those different sectors? Because you mentioned healthcare, you mentioned climate or food, things like that. So what impact has genomics had onto those areas?
We can cherry pick a few examples sector by sector. So if we begin with healthcare, where genomics has played the largest role so far, you kind of have to remember that in majority of the cases, if you do whole genomes or whole exomes, what you're trying to look for is a single cause, maybe a point mutation or a deletion that has occurred somewhere. And what you really want to do is identify those point mutations, because that has direct impact on the healthcare of an individual. In some instances, you look at research architecture, whereby you want to analyze genomes of hundreds and thousands of people to understand why some people respond to a specific drug and some people don't. And in some instances, this is where slowly you start to creep into point of care testing, whereby if it's a single mutation that you're trying to test every now and then in a huge number of individuals, then this sort of technology comes into play. Moving on to the food or agricultural sector, then you're talking about trying to understand why a certain variety of crop is more resilient to huge fluctuations in climate change that we are seeing these days. So understanding those traits become very, very important, because nowadays you want to have a good yield of a crop, but also at the same time, something that is more resilient to all the calamities that are happening around, or all the big fluctuations. So genomics is helping us to understand that and make better food for us. Moving on to trying to understand pandemics. So COVID-19 is a wonderful example where genomics really came to the rescue. Never in the history of mankind has anybody made vaccine within 1 year period. I mean, come to think of it, a normal time span is what, 10, 12 years, when you would first understand the architecture of a virus or a bacteria, and then you do phase 1, 2, and 3 trials, and then put it out. It was for the first time whereby even before something COVID-19 was declared pandemic, we already had the genetic architecture of COVID-19 virus. So in January of 2020, people had already started designing new vaccines against it. And by March, we were ready for phase 1 trial. That's a massive pace of acceleration that has occurred. And moving on to the infectious disease theme itself, we see a massive role of genetics or genomics in trying to understand which medication to give. So TB is a very big issue in the world these days, especially now that a lot of multi-drug resistance or total drug resistant TB are coming through. So genomics helps us to understand what type of resistance does a particular bacterium have in a given patient. So accordingly, we can start to target specific drug to that patient. And of course, oncology is one of the prime examples where genomics has driven revolution in terms of the medication we are given. Earlier, you would give medication kind of like a one-size-fit-all approach. You give the same medication and then you see which one is responding, which person isn't responding. Today, however, you give the drug based on what genetic architecture or mutation is present in a particular tumor. And accordingly, you give the medication so you get best response out of it. So you can see it has played a massive role.
Yeah, that's really one of your areas of speciality, right? When I was reading out, when I was talking, when we first started, chemo prevention, right?
Absolutely.
Is doing things like that. And you hit a very interesting point around, every time I do one of these, I'm not going to talk about the pandemic. I'm not going to talk about the pandemic. But you just tend to, you always just tend to come back because it's just so prevalent in everyone's mind. You hit how quickly vaccines were generated, tested and then generated, all that in silicon design work. how many crazies I've had to speak to on my life who are conspiracy theorists that you meet in the street. You go, there's no way you can do it. And they don't understand until you explain technology and where technology was, which is their baseline, to where it is today. And your ability to process that level of data, to make insight, to make clever, smart insight into that level of, with that level of data, to bring a product to market that's life-changing. So this is the wonder that I think of technology.
So, Sinisa, based on this, what sort of technological revolutions do you see in computing coming these days that can help drive the revolution even further?
Well, look, as you know, we fundamentally understand biology and genetics better now than we ever have before. And it's opening doors to numerous benefits that were, beyond our reach. You just spoke about them, right? Sustainable, efficient crop productivity, genomics tools, not genetic tools, but genomics tools, which increase animal resilience, being able to do all of this population health testing for genetic anomalies, etc. And this is all driven by these technology advancements that I just sort of mentioned in between, GPUs, accelerated technology. But as these systems get bigger and bigger and bigger, we have to start implementing ways to sort of cut down or to focus on, I guess I'm going to call it climate and environmental. So as we do all of that technological work, all that algorithmic mathematical functionality, you have all of this other technology around it that generates heat, sucks power, needs cooling. And so to do that, we implement water cooling from this technology called Neptune. And so we have all of these types of things. We work very tightly with our software development teams. We do, other organizations do the same, where you build in lots and lots and lots of different, efficiencies into our technology base. And all of this really gets driven into how we affect, it sounds dramatic, how we can affect humanity in a very, very positive way. When I think about GHOST, which I've mentioned before, and I think about sequencing and time to data, this for me is one of a really, I guess, the most exciting place for me as I look for sort of future forward. It's this precision patient care. And that's most exciting, right? Building a genetic diagnosis would allow for faster, more accurate care of patients. You just mentioned it a little while before. Yeah. If I used one specific example, myocarditis as an example, right? Happens when immune cells swarm a heart. It's often triggered by a virus or some other external, bodily stress, I guess you want to call it. Usually that's treatable by drugs. I'm just going to say, I'm not a doctor, but that's a treatable condition, usually when it's caught. The other cause, or I'm going to call it a symptomatic cause, is genetic. It's a genetic anomaly. And that particular cause, the genetic anomaly that causes heart failure or this myocarditis or symptomatic of that, is only effectively treated by heart transplant. So I was reading an article only about 3 weeks ago, and there was a 13-year-old child that represented symptomatically of myocarditis. Now, it took the doctors a period of time to diagnose that. And they did that by sequencing, and they did that by looking for the genetic anomaly, and they found it. And so this child was then put on a heart transplant list, and luckily for him, and God bless him, he received a new heart, saved his life. Now go back 3 years, that child would be dead today.
That's a very interesting point you make, Sinisa, actually, because now these new trials are coming up, and I know Rady's Children's Hospital in the US, they have really adopted genomics revolution to the core of their healthcare delivery, whereby if a sick infant is walking through the door, and it's just few days old, the first thing to do is carry out whole genome sequencing. In fact, they actually own Guinness World Book record of doing whole genome sequencing and reporting disease-causing mutation within 20 hours. That's groundbreaking. And based on the results, they actually have managed to change treatment and save more than 100 kids' life.
And that's the point. I think that's the point of all of this. That's the point of technology. Technology is not to replace human beings. It's to make our lives better, make us more sustainable, make humanity better. And so, look, given that as an example, and just to follow on from your commentary, what does your crystal ball say? What smart technology breakthroughs could we expect in genomics in the coming years? What do you think?
See, in genomics, the problem now is not data generation. So like I said, 30, 40 years ago, the problem was how much data you could generate. We have kind of broken that barrier. The next barrier actually lies in analyzing and interpreting all of that data. To give you an analogy, there is a world record for the longest traffic jam in the world. That was in China. That was more than 100 kilometers long. It took them more than 4 days to clear that traffic jam out. And I think we are coming to a point whereby we are having a similar traffic jam happening in genomics. You can generate tons of data, but to analyze it and interpret it is going to be the big challenge going forward. And this is where the next round of revolution really lies, to try and understand how to identify, to cherry pick this mutation that is leading to a disease in an individual, to try and understand why a particular trait or a disease happens in a particular community. So you can start to give different interventions based on where a particular disease is. You can try and start to analyze how we interact with our environment, how we interact with food that we eat. And there will come a point whereby we'll have our data stored in a cloud or a server somewhere, and we can simply bump our wristwatches or something of that sort to try and understand before two people get together, hey, would our future kid be having one of the nasty diseases whereby they end up dying? We are slowly coming to that point in our clinic, whereby patients are requesting, before we have a child, we want to know what carriers, what disease carriers do we have in our genome. So that is going to be the next round of revolution. The food that we eat is going to be going through a round of revolution as well. Like I gave an example, all the big fluctuations that we see in our environment today, our crops have to be resilient to that. And to do that, we have to understand what really makes a crop resilient to a given environment, to pest, to rising temperatures. And for that as well, we need the sort of computational architecture that ghost architecture that you just described, something that is fast, that is efficient, and can deliver the results in the shortest amount of time possible.
Yeah, amazing. You've hit so many. Look, you've hit so many things just in that last statement, let alone the rest of the session this morning, that it's made my head spin. Right? I think I said when I started, this is going to be quick fire. Look, clearly, you're very passionate. Your knowledge is so deep that it again, I bow. But look, I think the world is clearly on a precipice, right, of this accelerated advancement, as you're talking about. We're seeing some very exciting and fundamental changes, again, to address what you said, on how we attack disease, how we address climate, how we address food, how we address animal husbandry, how we do all of these things to make life sustainable in the future, but also protecting the planet we live on, because we only live on one, right? So I, for one, look, I'm incredibly excited to see what the next level of Star Trek's going to do for us. And I wanted to thank you again, really, for being on today. But more than that, thank you and your peers, right? Your continued research efforts using technologies, as an example, GHOST, high performance computing from Lenovo, artificial intelligence systems, is really making that difference, right? This visualization, this simulation, the in silicon work that you and your research colleagues are doing on a daily basis is just going to make life better for everybody, right? And I think our world, or at least my world, after this discussion today, has just become a little bit brighter. So thank you for today. Really appreciate your time. I know you're super busy, but I wanted to thank you for that.
Thank you, Sinisa. And I just wanted to say one thing for closing remark. I hope you wouldn't mind. That this entire revolution that we have discussed today has been possible not because just biologists or technologies that are coming in, but it's a whole workforce coming from that are trying to break different silos. So physicists, mathematicians, chemists, they're all coming together to make this revolution happen, to make lives better for everyone. And it's a massive thanks to one and all who are doing this wonderful work across the world. And thank you to you, Sinisa, for this wonderful fireside chat, and the Lenovo team for having me today.
You're welcome. And I don't think I could have closed it any better, Harsh. Thanks so much. I really appreciate it. I'll see you real soon.
See you real soon.
Bye.